Ebola, Spanish influenza, bubonic plague, AIDS. These diseases have two things in common. First, they're deadly. You don't need a doctor to tell you it's bad news if you get one. But second, and of most interest to me in my PhD, is these are all species-jumping pathogens, or zoonotic diseases. So zoonoses are diseases that leap from animals into humans. I study the animals these pathogens come from, what we call wildlife reservoirs. Reservoir species are the long-term natural carriers for zoonotic diseases, and my research addresses a particular group of reservoirs, bats. Now, bats are carriers for things like rabies, Nipah, Hendra, SARS, Marburg, and possibly Ebola. We also keep discovering new things in them that may one day be able to cross into humans. But despite carrying so many diseases, bats rarely suffer many negative effects, and we don't understand how they can do this. Now, it's been suggested that perhaps the unique trait of flight is playing a role. During flight, metabolic rates and core temperatures go up, approaching the range seen in you or I when we get a fever. Now, these temperature spikes could be helping bats to control infections, either by knocking down virus levels or speeding up immune function, allowing bats to tolerate pathogens or repair their damage. To test this hypothesis, I'm using a combination of approaches. Through mathematical models, I'm exploring how temperature changes affect the outcome of viral infections in bats, but I'm also making comparisons among species to see which other traits like wing morphology or diet may best explain which of the existing 1,300 species of bats are more likely to carry zoonotic diseases. Finally, I'm looking at how social behaviors affect disease spread in populations. And through this, I hope to help us better understand why bats seem to be so good at carrying so many diseases. Now, although only a handful of bat species carry anything that's a real threat to humans, understanding the ecological traits that allow bats to carry pathogens and, more broadly, the traits shared by all reservoir species is an important first step towards predicting zoonotic emergence events and minimizing their effects. Now, more than ever, zoonotic diseases are a threat. We are seeing more and more zoonotic emergence events, and our globe is as connected as it's ever been, making us more vulnerable to global pathogen spread. In fact, many people believe we are simply waiting for the next big one, a zoonotic pandemic of global proportions. It's scary stuff, but could you imagine the lives we could save if we could use ecological knowledge to forecast and prevent the next big one before it even occurred? Thank you.